Welcome PCS members and friends to our today's IBS PCS seminar. It is a great pleasure to have with us today Dr. Wouter Buijsman, excuse me, my pronunciation, from Ben Gurion University of the Negev in Israel. And I would like to invite our scientific host, Alexei, to introduce our speaker. Please, Alexei.
Okay, yeah, thanks, Dylan. So let me reiterate. So we have with us today Wouter Buijsman from Ben Gurion University of the Negev. And he's going to talk about circular Rosenzweig-Porter random matrix ensemble. Let me briefly introduce the speaker. So Wouter received his PhD in 2020 at the University of Amsterdam and has then moved to his current place, the Ben Gurion University of the Negev, and he's generically interested in breakdown of ergodicity in quantum many-body systems, localization, random matrix theory, and quantum thermalization, as you can already partially infer from the title of his talk. And so with this, please, Wouter, the screen is all yours.
Okay, thank you very much for the kind introduction and the invitation. Okay, this talk will be about the circular Rosenzweig-Porter random matrix ensemble. And this is a unitary equivalent of the classical Hermitian Rosenzweig-Porter random matrix ensemble that I proposed last year together with Yevgeny Balev in this article in Sci-Post Physics, which will also serve as the main reference for this talk. Okay, here you see the outline. First, I will provide, let's say, a basic broad introduction to quantum ergodicity, the breakdown of quantum ergodicity, and many-body localization. After that, I will briefly outline, let's say, the connection between quantum ergodicity and random matrix theory. So let's say why it's useful to use random matrix theory to describe and to understand quantum ergodicity. After that, I will discuss the Rosenzweig-Porter random matrix ensemble. I'll go a bit over the motivation, why it's constructed, the actual construction of the ensemble, and some of the basic properties. And then I will go a bit more in depth to the level statistics and the fractality of eigenstates. After that comes the main part of this talk, the circular Rosenzweig-Porter random matrix ensemble. We propose this using a technique known as Dyson Brownian motion. So first I will briefly outline this. And then with our knowledge of Dyson Brownian motion and the Rosenzweig-Porter random matrix ensemble, we are ready to let's say define the circular Rosenzweig-Porter random matrix ensemble. Along with the definition, I will also, let's say, argue that this ensemble shares the properties of the conventional Rosenzweig-Porter random matrix ensemble, and I will verify this numerically. And this talk will be closed with conclusions and an outlook. Okay, first quantum ergodicity. Let's say in the field of quantum ergodicity, quantum gales, we essentially make a distinction between two types of systems. On the one hand, we have non-ergodic quantum systems which do not thermalize. And on the other hand, we have ergodic systems which do thermalize. And these two classes of systems have vastly different properties. Non-ergodic systems have Poissonian level statistics. So let's say when we take the Hamiltonian, we diagonalize it and we look at the statistics of the eigenvalues, we see that these are uncorrelated. Here in the right figure, you see an example. You see, let's say, a spectrum with a certain lower bound and a certain upper bound. The levels here are just sampled independently from the uniform distribution from this lower bound to the upper bound. And what you see is that there's essentially no structure in this spectrum. You see sometimes levels are very close. Let's say this sign means there are two levels. You also see the levels are very close. Well, sometimes there are very large gaps. Yeah, there's no regularity. And the same you see holds for the prime numbers. And when you, let's say, make the spectrum of an integrable, or sorry, a non-ergodic quantum system, then you see the same structure. When we look at ergodic quantum systems, let's say, for example, here you have the Sinai billiard, then you see that the structure is much more regular. Let's say the Sinai billiard is essentially a two-dimensional infinite leap quantum well with a very irregular shape. The system is ergodic, and yeah, what you see is that although sometimes levels are close to each other, it does not happen as often as the case for the non-ergodic spectra. And besides that, you also see that the large gaps are vanished. And this is, let's say, essentially a consequence of the fact that the levels know about each other. Let's say people tend to say that they repel each other. So, okay, when we just have the spectra, you see there are really two different classes. Next, we also see that ergodic and non-ergodic systems have very different types of eigenstates. Here you see again a quantum billiard, let's say a particle in a billiard. Here you see an ergodic eigenstate. You see the particle is let's say that the wave function is neatly spread out over the full system. And here you see a non-ergodic eigenstate, and here you see it's very strongly, let's say, localized near a certain part of, let's say, all possible space. Yeah, in some sense, this is a bit of an unfortunate example because, let's say, typically we say that an entire Hamiltonian, let's say, is non-ergodic or ergodic, meaning that all of the eigenstates are either ergodic or non-ergodic. This is just one of the very rare examples where we have both non-ergodic and ergodic eigenstates. And maybe you recognize this figure from the context of quantum many-body cars, which is, let's say, a field in its own right. Okay, generically, quantum systems are ergodic, unless, let's say, there is some specific property mechanism active that, let's say, makes the system to escape ergodicity. And there are, roughly speaking, three of these mechanisms. One is integrability, one is Anderson localization, and one is many-body localization. Integrability was, let's say, essentially introduced by Hans Bethe in 1931, and he found out that certain interacting quantum many-body systems have an extensive number of conserved quantities, which means that the Hilbert space decomposes in, let's say, a number of sectors, which is a number of symmetry sectors, which is equal to the number of eigenstates to the dimension of the Hilbert space. Which means that, let's say, in some sort of a natural basis, the Hamiltonian is diagonal. And of course, then eigenstates do not spread out over all Hilbert space. They are really localized. This, however, requires typically fine-tuning of the Hamiltonian. Here in this figure, you see a nice example of an integrable system. This is a quantum Newton's cradle. What is this? Two quantum particles in a harmonic trap. And what the people did here, let's say this is real experimental data. They let the system evolve over time, and they measure the position of these particles. And what you see is really, let's say, the particles approach each other and they go away from each other again. And you really see, let's say, a repetition, let's say, a memory of the initial state and recurring dynamics. And this is something which will be completely impossible if the system will be non-integrable, because then, let's say, the system will immediately relax to a thermal state. Okay, a second mechanism to escape ergodicity is Anderson localization. This is what we see in non-interacting lattice systems, spin-on-out lattice systems. And what we here have is that because of disorder, some certain inference phenomena occur by which eigenstates become spatially localized. And then again, what we have is, let's say, the eigenstates are spatially localized. They don't spread out over the full system. And the system is just non-ergodic. And this was found by Anderson in 1958. It was already asked in the early days of Anderson localization whether this mechanism could be extended to interacting quantum many-body systems. And this is a very difficult question, it turns out. But eventually it was found by Basco, Lyon, and Altschuler in 2005 that the answer is essentially yes. They proposed that for certain interacting many-body systems, the low the lowest states remain localized. And later on, let's say, when people jumped on this with numerical studies, they found out it's actually much more robust than what was proposed by Buijsman and Altschuler. And I'll come back to that on the next slide. Yes. Okay, now I step away, let's say, from many-body localization as it was proposed by Buijsman and Altschuler, and now I go to, let's say, the modern view, you can say. We typically study this numerically, although also analytical studies have been performed. Often the focus is on a Spearman half chain with short-range interactions and random on-site disorder. This is typically referred to as, let's say, the standard model of many-body localization nowadays. Here you see the Hamiltonian. It's we have nearest neighbor spin interactions, and there is a potential term with a different potential, let's say, on each side. And these potentials are sampled from a uniform distribution ranging from -W to W. And these are sampled independently, so there is a disordered system. Because of this interaction term, the system is non-integrable, and yeah, we cannot say anything about it analytically, basically. Here in this figure, you see a phase diagram that has been obtained in 2015. On the horizontal axis, you see the disorder strength. So what is called H here is the W here. And on the vertical axis, you see the energy density. So let's say the lowest line is the ground state, and the upper limit is the highest excited state. And let's say the middle of the spectrum is here. And what was observed is that if the disorder strength is, let's say, not too high, below 3.6, 3.7, then the system is in ergodic state, while above this disorder strength, the system is in a many-body localized state, which is a strongly non-ergodic phase. And just as an illustration here, yeah, suppose that we have this system and we initialize it in a system with, say, spin up, spin down, spin up, spin down, spin up, spin down, alternating. And we let it evolve over time. Okay, when we are in ergodic phase, then the system immediately forgets, let's say, about this initial state. And the density, let's say, the spin density becomes completely uniform. Let's say each particle has a probability 0.5 to be up and a probability 0.5 to be down. Well, in the many-body localized phase, the system does not remain in the same state. This is the same as what you saw in this cradle on the former slide. But still there is, let's say, a memory of this state. So you see still there is, let's say, yeah, still some, the probability for the even sides to be up is larger than 0.5, or for the odd sides, it's smaller than 0.5. Yes. Okay, this brings me to another, which is seemingly a bit unrelated topic, the relation between quantum ergodicity and random matrix theory. Let's say, the first slide you saw that, let's say the quantum ergodic and non-ergodic systems have different types of level statistics. And this was formalized by Bohigas, Giannoni, and Schmidt. And what they proposed, by what they conjectured, was that quantum chaotic systems, so quantum ergodic systems, universally have Wigner-Dyson level statistics. And what Wigner-Dyson level statistics these are the level statistics of the Gaussian orthogonal random matrix ensemble. Let me briefly go to the Gaussian orthogonal random matrix ensemble. This is an ensemble consisting of symmetric real-valued matrices. So you can think of it as a random matrix model for Hamiltonians with time reversal symmetry. This is the probability distribution. And what makes this random matrix model special is that it has no preferred basis. Which means that if we take an orthogonal matrix R, and let's say we use this to perform a basis transformation on this probability distribution, then the ensemble remains the same. Or more concrete, if we take many samples from let's say the Gaussian orthogonal ensemble, on all samples we form the same basis transformation, then there is no way to distinguish, let's say, between the original samples from the Gaussian orthogonal ensemble and the transformed samples of the Gaussian orthogonal ensemble. They both have the same properties. So in this sense, you can say it is a maximally chaotic random matrix model for a time reversal, Hamiltonian system with time reversal symmetry. How this is quantified is by looking at the level spacing distribution. So you take the spectrum, the eigenvalues, you look at the spacings between consecutive levels, and you make a histogram of this. And you normalize them such that the average spacing is 1. And what you see is, then you can draw this type of histograms, and indeed you see for the Sinai's billiard and the Gaussian orthogonal ensemble, you see good agreement. Okay, slightly earlier, it was already proposed by Berry and Tabor that it was conjectured actually that Brownian level statistics are universal for non-ergodic quantum systems. So if we then want to make a random matrix model, we just take a diagonal matrix with independent elements. Then the spacings are Brownian, then you get this type of histogram. And indeed, what you see in agreement with the spectra I showed before, that for the non-ergodic systems, the probability both to find, let's say, levels very close to each other, so very small spacings, is much higher than it is for ergodic systems. But also the probability to find levels very far apart from each other is much higher for non-ergodic systems than it is for ergodic systems. Okay, now the Rosenzweig-Porter random matrix ensemble. Up to now, I essentially talked only about systems which are either fully ergodic or fully non-ergodic, let's say. So they either had the Dyson level statistics or Brownian level statistics, this level statistics of the Gaussian orthogonal ensemble or the Brownian distribution. It was observed by Rosenzweig and Porter that in practice, many realistic quantum systems, such as heavy atomic nuclei, they show some sort of intermediate level statistics, which are neither Brownian nor Wigner-Dyson. Okay, here in the right figure, you see some examples. What I did, they took data for many different types of atoms and they somehow grouped them. And what you see here is that in this group, the level statistics are, let's say, close to Brownian, but not fully. Here you see the level statistics are a bit, let's say, in between Brownian and Wigner-Dyson. And here they are close to Wigner-Dyson, but again, not fully. You see in particular here, let's say the probability to find very small level spacing is let's say, higher. And also to some extent, the probability to find very large level spacings is higher. And what they did, they proposed a random matrix ensemble to describe this type of intermediate level spacing distributions. And this is what they came up with. The ensemble consists of matrices, which are the sum of two terms. On the one hand, you have a diagonal term with independent elements. So if you just, let's say, ignore the second term for the moment, if you would study the level statistics of this system, you get Brownian level statistics. And second, there's a Gaussian orthogonal ensemble term. Let's say, and if you ignore this term, then if you make this prefactor, let's say, very large, then you will recover the Wigner-Dyson level statistics. And there's let's say, a prefactor in between, which either with the tuning parameter gamma, which either let's say, makes the Brownian term or the Gaussian orthogonal ensemble term dominant. Okay, it's not, let's say, it is a bit of a, it's a term which involves here, n is the dimension of the matrices. This is just to make sure that, let's say, the statistics, the level statistics and the eigenvector statistics of the ensemble do not change under, let's say, they do not change when we change the dimension of the matrices. And an important thing to note here is that this ensemble has a preferred basis, which means that let's say it is not like the Gaussian orthogonal ensemble invariant on the basis transformations. And although this might seem unimportant, it is for analytical purposes, it is very important, because essentially everything that we can say about the Gaussian orthogonal ensemble somehow utilizes that the ensemble is invariant on the basis transformations. So this ensemble is kind of more difficult to study analytically. Okay, despite that it is difficult to study this, the Rosenzweig-Porter ensemble analytically, people still manage to get analytic results in a thermodynamic limit. It was found by Altland, Janssen, and Shapiro in the 1979 that for gamma smaller than 2, the system has within Dyson level statistics, while for gamma larger than 2, level statistics are Brownian. And they did this using diagrammatic perturbation theories. It's quite a technical and involved study. Yeah, quite later in 2015, Kravtsov-Kajmovic and some Kajmovic and some other people, they studied the eigenvectors, the eigenstate statistics of this ensemble. And what they found was that essentially the ensemble has 3 different phases. There's an ergodic phase for gamma is smaller than 1. Here the eigenstates are fractal dimension 1. There's a fractal phase in which, let's say, the fractal dimension of the eigenstates is 2 minus gamma. So let's say if you go from gamma is 0 to 1, it's 1. If you go from 1 to 2, it linearly decreases to 0. And when it's larger than 2, then it remains 0. And just as a reminder, let's say this is the definition of the fractal dimension dq. The fractal dimensions carry an index. Typically, however, the focus is only on q equal 2. When we set q equal 2, here the left-hand side, if this is an eigenstate, gives the inverse participation ratio. And on the right-hand side, we have n to the power minus the fractal dimension. So the fractal dimension says, let's say, how a wave function is spread out over the full Hilbert space as a function of the matrix size. And you can show analytically, and this was both done by Kravtsov and Kajmovic and co-authors, as well as by Bokomoni and Sieber in 2018, that these fractal dimensions do not hold only for the first fractal dimension with q equal 2, but really for all fractal dimensions. Okay, and the motivation to let's say to study the random matrix ensemble by these people was essentially that they observed numerically that it can serve as a random matrix model for the many-body localization transition. Indeed, here you see a phase diagram which was obtained numerically, let's say in 2017. Okay, this is from a review article, so most things were known already a bit earlier. Okay, on the horizontal axis here you see the disorder strength again, this W. The many-body localization transition is around 3.6, 3.7. Here it's estimated slightly lower. And what we see again is that, like for the Rosenzweig-Porter random matrix ensemble, that at low disorder strengths we see the states, eigenstates are fractal dimension 1, while for a stronger disorder, let's say the fractal dimension is smaller than 1, and in the many-body localized phase, the fractal dimension equals 0, which is not given here, but is claimed in the paper. We see a slight deviation when we look at the eigenvalue statistics or level spacings. Indeed, let's say at weak disorder, so in the ergodic phase, they observe within Dyson level statistics. For the Rosenzweig-Porter random matrix ensemble, you really go, let's say, from within Dyson level statistics in this entire regime to Brownian level statistics immediately here, while, let's say, for the standard model of many-body localization, we see some sort of intermediate level statistics as well. So let's say it is, let's say the Rosenzweig-Porter model is, let's say, a toy random matrix model for the many-body localization transition, but it's not perfect. yeah, and this also is of course obvious. It does not match when we look at the transport of energy and the transport of spin or particles. Of course, because let's say the Rosenzweig-Porter random matrix ensemble does not have a notion of locality, so there's no notion of, let's say, diffusion in the type of case. Okay, so let's say the Rosenzweig-Porter random matrix ensemble is a random matrix ensemble that more or less is able to describe the many-body localization position, but it's not perfect. And this motivated several people, let's say, to come up with generalizations of this ensemble. Examples include the Lévy ensembles by Montes and Biroli Tasia. Let's say here, let's say the off-diagonal elements of the ensemble have a more heavy tail by which you can, let's say, shift this phase, and you can induce real multifractality instead of monofractality. In the same spirit, people proposed a log normal Rosenzweig-Porter ensemble where also, let's say, the off-diagonal elements are more heavy-tailed, but in a slightly different way. Yeah, and besides that, there are also, let's say, different types of Rosenzweig-Porter random matrix ensembles that have been proposed. Let's say, like I am now proposing a unitary Rosenzweig-Porter random matrix ensemble. But for example, there also a non-Hermitian Rosenzweig-Porter random matrix ensemble has been proposed. And if you go to the reference list of this paper, you see that these people are also working on some sort of a more sophisticated circular Rosenzweig-Porter random matrix ensemble. So probably at some point there will also be, let's say, a mixture between, let's say, these generalizations and the circular Rosenzweig-Porter random matrix ensemble that I will propose in a second. Okay, what is, yeah, okay, the overall goal, let's say, of what I did was to propose a circular Rosenzweig-Porter random matrix ensemble. And you might ask, okay, why would you do this? And the motivation is that up to now, let's say, you saw there is many body localization for Hermitian systems, for static systems. But many body localization has also been observed in Floquet systems. And these systems, let's say, have a time-dependent Hamiltonian, which, let's say, repeats itself in time. And because the Hamiltonian is time-dependent, it is not very conventional, let's say, to describe these systems by the Hamiltonian. Instead, we describe them by what is known as the Floquet operator, which is the time evolution operator of this Hamiltonian, let's say, over a single cycle. Okay, these Floquet operators have completely different, okay, let's say from a mathematical point of view, they are very different from Hamiltonians. They don't have eigenvalues, but they have eigenphases, which are, let's say, on a complex unit circle. They still have eigenstates. So yeah, oh, sorry, where was, yes, here. So this means that if you want to propose a circular Rosenzweig-Porter random matrix ensemble and a unitary Rosenzweig-Porter random matrix ensemble, you really need to do something non-trivial, let's say. Okay, we see that the Floquet many-body localization systems that, yeah, Floquet many-body localized systems, they have been proposed, for example, in these references. They typically obey time reversal symmetry, so that will also be the case on which we focus, which means that the Floquet operator, the single cycle time evolution operator is symmetric, it's unitary symmetric. Okay, so now let me go to the next slide. Now comes the main part. Okay, how can we construct a circular Rosenzweig-Porter random matrix ensemble? The technique that we use for this is something known as Dyson Brownian motion. This was proposed by Dyson in 1958. But before I go into details about this, let me briefly comment on how the Gaussian orthogonal ensemble is actually constructed. Okay, before when I introduced the Gaussian orthogonal ensemble, okay, I mentioned, let's say, the probability distribution for the matrices, but not, let's say, how you can actually construct these matrices. And you can construct them, let's say, quite easily. Namely, you take a matrix, a symmetric matrix, and you fill them just with independent Gaussian distributed elements. And these Gaussian distributed elements all have mean 0 and variance sigma squared. And the variance is 1/2 for the off-diagonal elements and 1 for the diagonal elements. And then you can easily show that this random matrix ensemble, let's say if you sample many of these matrices, exactly obey the properties of the Gaussian orthogonal ensemble. Okay, what is Dyson Brownian motion? That is essentially the overall idea is to make the matrix, the elements of the matrix elements, to make them time dependent. So what we do is we have a matrix M, which depends on t, and the matrix at time t plus, let's say, some infinitesimal small time step dt is given by the original matrix plus the square root of dt times a GOE matrix, a sample from the Gaussian orthogonal ensemble. Which means that, let's say, for a given matrix element at each time step, we add a small Gaussian distributed value with variance dt and mean 0, which means that the elements of this matrix perform independent Brownian motions. And this allows us to define a parameter-dependent extension of the Gaussian orthogonal ensemble. Namely, if we take some sort of a we can take the initial matrix in whatever form we wish, and we can let the time run to every value that we wish. And let's say only when we run time to infinite, such that, let's say, this term is completely dominant over this term, we recover the Gaussian orthogonal ensemble. In other cases, we obtain some sort of parameter-dependent extension of the Gaussian orthogonal ensemble. On the first sight, let's say, it might seem to be overcomplicated to perform, let's say, this Brownian motion of the matrix elements. If you can instead just immediately write down this, I mean, in order to construct matrices like this, you don't need to go over all these super small time steps. However, let's say in the context in which Dyson is proposed this initially, let's say it makes sense. So it seems overcomplicated here, but in the context of the circular Dyson Brownian motion, next slide, we will see that it is useful. And this construction, what's an important point, allows us to construct, let's say, to reconstruct the Rosenzweig-Porter random matrix ensemble. So we can write the Rosenzweig-Porter random matrix ensemble as the outcome of a Dyson Brownian motion process. To be specific, if I go back a few slides, yes, here we had the construction of the Rosenzweig-Porter random matrix ensemble. Here you have this diagonal term, prefactor, and the GOE. You might already recognize the same shape, let's say the same form. Yes, if we take the initial state as the diagonal, this diagonal matrix, take the time evolution just as here, and we evolve this system from time 0 to time 1 over n to the power gamma. Then here you get, let's say, this 1 over n to the power gamma gets square root here. And so indeed you recover the Rosenzweig-Porter random matrix ensemble. Okay, let's say the usefulness of the Dyson Brownian motion becomes clear, let's say, when we look at how this extends to circular ensembles, so unitary ensembles. This was proposed by Dyson actually in the same paper. So there you can look up details how this works. What essentially is the idea is that, okay, as said, for Hermitian matrices, we have the time evolution looks like this. For unitary ensembles, the time evolution is a bit more complicated. What we do then is we add a small part du, which is given by, let's say, for let's say extremely small dt by a Gaussian orthogonal ensemble times a factor I, transformed to some with some transformation applied to it. And these matrices V are obtained from U at time t as V times V transpose. And these matrices are only required to be unitary. Well, let's say U is required to be unitary symmetric. And it turns out that you can make, let's say, this decomposition U is V transpose, of course, in different ways, but they are all equivalent because of the basis invariance of the Gaussian orthogonal ensemble. Let's say if you have two different ways of making this decomposition, then we can incorporate the difference, let's say, in the matrix sample from the Gaussian orthogonal ensemble. So you can take, for example, just V is the matrix square root of U. Yeah, and what you can show with this is that if you, let's say, perform the Brownian motion over time, the Dyson Brownian motion or the circular Dyson Brownian motion, that the dynamics of the eigenvalues and the eigenphases are really the same. You see here, these first terms are the same. Here, of course, because, let's say, the eigenphases are, let's say, 2 pi periodic, this term does not translate exactly to this, but if you take a first order expansion of this tangent 1/2, you get here factor 2 and take this cancels against this factor 2, then you see that up to, let's say, many mean level spacings, you get really the same eigenvalue and eigenphase dynamics. And what you can show, which is not on this slide, is that you can derive similar equations, although they look a bit more complicated for the eigenvectors. These also evolve stochastically. Okay, now that we know how, and one point before I continue is that for the Dyson Brownian motion for Hermitian matrix ensembles, we can immediately, let's say, integrate it over time. Let's say we know the initial state, we know the time, and then we can immediately compose, let's say, the M evaluate at time t. For the unitary ensembles, this is unfortunately not the case. So then if you want to evolve it over time, you really need to go over all these small time steps. So the upshot is it allows us to define, let's say, a circular equivalent of Brownian motion, Dyson Brownian motion. The downside is that the evaluation, at least numerically, is kind of expensive. Okay, now that we know Brownian motion, Dyson Brownian motion for Hermitian ensembles, and circular Brownian motion, circular Dyson Brownian motion for unitary ensembles, we are in a place to define what we call the circular Rosenzweig-Porter random matrix ensemble. Okay, for the Hermitian ensemble, we have initially uncorrelated a diagonal matrix with uncorrelated elements. For the circular Rosenzweig-Porter ensemble, we also take a diagonal matrix, but with eigenvalues uniformly uncorrelated distributed on the unit circle. So both have, if you look at the level spacing statistics, both have, let's say, Brownian level statistics and eigenvectors, which are basis vectors. Okay, these I already mentioned. An important point, if I go back to one slide, is that if we want the dynamics of the eigenvalues and the eigenphases here to be similar, we need, let's say, these terms to be, let's say, yeah, the same. And this requires that the density of states is the same, because if the density of states here differs from the density of states here, let's say then the average level spacings differ, and by that also these terms differ. So you need to define the circular Rosenzweig-Porter random matrix ensemble such that the density of states for the Hermitian and the unitary ensembles are the same. Everything I said up to now for the Hermitian Rosenzweig-Porter random matrix ensemble applies to the middle of the spectra. And then you can show that because, let's say, these elements are Gaussian distributed, and the addition of a small Gaussian orthogonal ensemble matrix does not influence the density of states, then the density of states in the middle of the spectrum is n over square root of 2 pi. Well, here we have m elements, then the density of states is equal to m over 2 pi. So that, yeah, we want these quantities to be the same. And by that, you need to choose m is the square root of 2 pi n. So yeah, if we choose this number of levels, then the dynamics of the Hermitian and the unitary Rosenzweig-Porter ensembles are really the same. And if we evolve them up to the same time, then we really get two of the same ensembles. Of course, you can also take here the number of levels n and then, let's say, incorporate it in the time until which you evolve an ensemble, but this is a bit more complicated. Okay, so now I've proposed the Rosenzweig-Porter random matrix ensemble, circular Rosenzweig-Porter random matrix ensemble. I hope that you're more or less inclined to believe that it shares both eigenvalue and eigenvector statistics with the Hermitian Rosenzweig-Porter random matrix ensemble. Yeah, now will try to convince you even more by investigating this ensemble numerically. What we did first was we looked at the level statistics. And in order to investigate this, we looked at the average ratio of consecutive level spacings. I guess most of you have heard about this at some point. For those who didn't, what we essentially do then is, instead of looking at the distribution of the spacings of consecutive levels, we take, let's say, we look at 3 levels, and then we have 2 spacings. We look at what is the smallest spacing, and we look at what's the largest spacing, and we divide them on each other. This has 2 advantages. One, this ratio is independent of the density of states because it's the same for both level spacings. And second, it allows us to, let's say, to quantify the level statistics. And what we find is that if you have written Dyson level statistics, then we find an average ratio of consecutive level spacings, which is, let's say, 0.53. While if we have level statistics which are Brownian, then we find 0.39. So there's quite a significant difference between them. And just recall this paper by Altland that I mentioned before. So for gamma smaller than 2, we expect the average ratio of consecutive level spacings to be 0.53 for gamma smaller than 2, and it's expected to be 0.39 for gamma larger than 2. Okay, here you see in the left plot, you see the results. We studied this ensemble for dimension 250, 500, and 1000 in darker colors. And what you see is indeed at gamma equal 2, there is some sort of, let's say, a crossing point between, let's say, increasing values of the average ratio of consecutive level spacings and decreasing values. And we can not exclude that, or let's say, we can more or less assume that for indeterminate limits, this will go up to this line, and here it will go down to this line. And because we, let's say, need to fully involve this full Dyson Brownian motion process, let's say, it's quite a kind of a expensive numerical computation. So we were not able to go to very large system sizes, but at least you see that there's clearly a trend going towards what we expect. To make this claim a bit stronger, we also did a finite size scaling collapse. This was investigated by Pino and some co-authors in 2019. We have a first order phase transition, so nu equal 1 at the critical disorder strength, gamma equal 2. And what these authors found, more or less empirically, was that the size of the matrix here is given by the logarithm of the matrix dimension. So let's say this also illustrates that the convergence is kind of slow. And you see here, indeed, we observe, let's say, the same collapse as what they observed. So to conclude, let's say we have some numerical evidence that we indeed observe the same level statistics. Next, we focused on the eigenstate inverse participation ratio, which is given by the overlap of the eigenstates of the Hamiltonian with the basis states to the power individual elements to the power 4. So it's essentially the second moment of the second moment of the eigenstates. For gamma smaller than 1, we have fractal dimension 1, so we expect this quantity to scale as 1 over n. While for gamma larger than 2, we have fractal dimension 0, so then we expect this quantity to be a constant. In this plot, the upper plot, you see indeed there is again a a crossing point between, let's say, decreasing values and increasing values at 2. If we look here at the plot of n times the matrix dimension times the inverse participation ratio, then we see that for gamma smaller than 1, roughly, the inverse participation ratio is essentially a constant, and after that we also see some crossing point here, it increases. In principle, it will be possible to extract also fractal dimensions, let's say, from this data. We've tried it, but you get sort of actually the phase diagram with this fractal dimension that you expect, but this is kind of strongly sensitive to finite size effects, so that's why we didn't include it here. But if you want, you can just simulate this ensemble and plot it and see. There's also this recent preprint by Klemovic, in which he studied this non-Hermitian Rosenzweig-Porter ensemble. There they actually plot the second fractal dimension, and then you see essentially the same. You see more or less, let's say, the fractal dimension that you expect, except for some small deviations which you can attribute to finite size effects. Okay, finally, we looked at the structure of the eigenstates, which is in the context of the Rosenzweig-Porter random matrix ensemble known as mini bands. And what the overall idea is that we decompose, for a Hermitian system, the idea is to decompose Hamiltonian in a reference system and a perturbation, and then to expand eigenstates of the full system in the eigenstates of the reference system. So what we do then is, what you can do is you can make a plot, and on the horizontal axis take the eigenvalues of the reference system. So in the context of the Hermitian Rosenzweig-Porter ensemble, this will be the diagonal term. And then on the vertical axis to put, let's say, the overlap of the eigenstates of the full Hamiltonian with the eigenvectors of the reference system. And what you then intuitively expect is that the most significant contributions comes from eigenstates of the reference system which are close by in energy. So let's say this perturbation only hybridizes, let's say, eigenstates of the reference system which are close by in energy. And in quantum ergodicity, this goes under the name of bright weakness statistics. In the context of the Rosenzweig-Porter ensemble, this is also referred to as mini bands. These statistics are kind of generic for quantum thermal quantum many-body systems. for a beautiful reference of this, I would refer to this paper by Borgonovi and co-authors from 2016, which reviews essentially everything on this. When you have these statistics, what we have at the quantitative level is that the overlap of an eigenstate at an energy n with the overlap of an eigenstate of the reference system at an energy em0 is proportional, let's say, to the square of the energy difference between these two states plus some spreading width, and this all 1 over all this. So this is a Lorentzian shape. And this spreading width is obtained from Fermi's golden rule. And let's say it was shown actually by Bogomolny and Sieber in 2018 that these statistics also apply to the Rosenzweig-Porter ensemble, even let's say in the fractal phase. So not only in the ergodic phase, but also in the fractal phase. Okay, this is what we got numerically. This is, let's say, the same equation I showed before, but then with the energies replaced by the eigenphases, because now we are looking at the Floquet system. If you use Fermi's golden rule, then you can show that this is the spreading width. What we show here is the red curve is this expression with this spreading width, so there's no fitting involved at all. And the blue dots is what we get numerically for the ensemble. Here in the ergodic phase, what you see is that, let's say, eigenstates are really spread out over the full Hilbert space. So here we get really a flat curve. We see kind of good agreement. You see a slight deviation, which we can attribute to the fact that, let's say, instead of an infinitely wide spectrum which you have for Hermitian systems, now the spectrum is periodic. So let's say this type of shape needs to get some corrections, let's say, at the boundary. We also, and by the way, this is for matrix dimension 1000, the largest that we studied. This is what we get in the middle of the fractal phase. What we see here is, indeed a very strong peak. So eigenstates are really, let's say, centered, let's say, within 0.1 radians, which is, let's say, more or less also consistent with what you would expect from theory. Here also you see a slight deviation. This is also, something that you cannot really avoid, because here, let's say, the spreading width is of the same order as the mean level spacing. So then you really get, finite size effect because of individual level spacings. Well, this theory essentially only works in a thermodynamic limit. So, there's a deviation, but this is also what you sort of could expect. Okay, this brings me to the final part of this talk, the conclusions and outlook. Okay, in summary, we have proposed a circular Rosenzweig-Porter random matrix ensemble, and when we look at the eigenvalues, let's say the eigenphases and the eigenstates, we get up to, let's say, reasonable precision what we expect from the theory. Then there is, let's say, some outlook, some things, suggestion for future research. It was proposed that many-body localization transition is multifractal. Let's say I quoted, let's say, this phase diagram some slides ago. More recently, more evidence, let's say, has been gathered that the many-body localization is indeed multifractal. And as you might have noticed, let's say, in the community of many-body localization also, the phase diagram is getting more and more complicated. So it will be interesting to see if we can come up with generalizations of this ensemble that we proposed here that cover all these things like multifractality, etc., etc. And second, kind of related, is that some generalizations of the Rosenzweig-Porter ensemble have been proposed. I quoted them a few slides before. And it turns out that even though these ensembles are more let's say, sophisticated, quite often we still can, at an analytical level, say quite a lot about them. Yeah, and that's what also be really interesting to see if we can, let's say, make circular analogues of these ensembles. And finally, a bit on a different route, there's also this field of random unitary circuits. And what we have there is, let's say, typically these circuits are, let's say, more or less maximally random. An exception is a figure you see here by Chandeluca and Cholker from 2018. And what they have here is let's say, what I wanted to do is to study, let's say, non-maximally chaotic random unitary circuits. And these blocks really indicate samples from their circular unitary ensemble. And in order to make the system non-maximally chaotic, let's say, they add these circles indicate dephasing blocks. And by tuning the strength of the dephasing blocks, you can, let's say, make this random unitary circuit either, let's say, let's say you can tune the degree to which it is chaotic. Yeah, instead of adding this type of dephasing terms, of course, you can also think of matrices which are not maximally random and which are, for example, sampled from the circular Rosenzweig-Porter random matrix ensemble. This might also be interesting to investigate. Okay, with this, I would like to thank you for your attention. And I would also acknowledge some people that were involved in this project. In the first place, my supervisor, Yevgeny Balev, who was really, let's say, involved in this project from A to Z, from the first idea until the final writing of the paper. Second, I would like to thank Ivan Kajmovic, who was involved mainly in a later stage of this project. And yeah, he's really an expert on this Rosenzweig-Porter and the matrix ensemble, and he came with quite a lot of useful suggestions and comments. And finally, I would like to thank Leah Santos from Yeshiva University in New York, who, let's say, knows a lot about these bright witness statistics and pointed out some interesting references to us, and we also had some useful discussions. Okay, let me thank again you for your attention, and I'm happy to take questions.
Thank you, Wouter, for this nice presentation. Let us thank our speaker. And we have time for questions. Perhaps let me start. Another possible way to introduce this ensemble, I guess, would be maybe to just consider a kicked system, to somehow have like for the Floquet picture, it kind of becomes easier because you don't need to do time evolution. If you just have a propagation for some time of, I don't know, GOE, and then do a kick with the diagonal maybe matrix.
Yes.
Numerically, it would be easier to treat.
Yes. I think numerically it will be easier indeed. Yeah, because you don't need to do the full calculation of all these small time steps. We thought about this type of things, but what I think can be difficult is that you really want to argue that let's say that you get the same statistics as for the as for the Rosenzweig-Porter random matrix ensemble, including, let's say, the fractality of eigenstates and so on. So then, let's say, the difficulty I think is mostly in let's say, how to choose, let's say, the Hamiltonians that you will take. But I cannot exclude that I think in principle it's possible, but in practice it can be tricky to find, let's say, the real Hamiltonians that you need to take for that.
To compare exactly.
Yeah. Yes.
Okay. Thank you. Weihua has a question. Weihua, please unmute yourself.
Okay. So my question is that how do we understand the chaotic properties of the correspond to the intermediate state?
Sorry, how do we understand what?
how do we understand the chaotic properties of the correspondent to the intermediate state?
The what type of properties? Sorry,
chaotic properties. Chaotic properties.
Chaotic. I guess chaotic.
Chaotic properties.
Yes. How to understand the chaotic properties of the
intermediate state. Intermediate between the Poisson and the GOE. How to understand that? I mean, the chaotic proproperties.
In this,
so it's like a classical fifth space. You have
yeah, how you can think of this is that the eigenstates occupy yeah, they're not, let's say, fully chaotic. Let's say they occupy really a small part of the Hilbert space. So in that sense, they are non-ergodic. But let's say if I go to this definition, let's say the degree to which an eigenstate is spread out over the Hilbert space, let's say, decreases with increasing Hilbert space dimension. So if I take a small dimension, then the state is reasonably spread out over the full Hilbert space. And if I take a very large dimension, then it is really not localized, but let's say confined to a small part of Hilbert space. However, let's say these states are still, let's say, overlapping enough, you can say, such that the Hamiltonian is not, let's say, diagonal in some sort of natural basis. And because of that, you still have within Dyson level statistics. Does this answer your question?
No, I don't understand. I still don't understand. So so you mean the part of the wave function is will have the ergodic properties, and part of the wave function will have the localized properties, and then they will show the intermediate state.
Let's say that they are sort of, yeah, the eigenstates are sort of intermediate. Let's say they don't occupy, let's say, on the one hand, if you have, let's say, ergodic states, then the eigenstates occupy, let's say, a non-vanishing fraction of the Hilbert space. Well, if they are localized, then they occupy, let's say, a small part which is essentially independent of the matrix dimension. So if I increase the matrix dimension, let's say, the state remains equally localized, the number of basis states that it covers. And fractal is something in between, let's say. So you can think of it either as, let's say, ergodic and non-ergodic to some extent. But yeah, the level spacing statistics are still within Dyson there.
Okay. Thank you. Thank you for the answer.
And we have a question also from Alexei.
Yeah, I mean, let me start by a quick comment to what Dylan was asking. Actually, that's what we're looking at right now. And so we're looking, we try to see if by making kicked system, you can construct unitary, non-ergodic unitaries. Let me call it this way. We don't know if they have a multifractal phase, but definitely you can get a localized phase. This is
I can expect it. Can imagine.
If I may add, you know that if you have kind of in a certain high frequency regime, so when the kicks are occurring with very high frequency, you can expand and get effective Hamiltonian, which will be just kind of strength of the kicks over the time period. So the part will be rescaled. So you should get in high frequency regime, you should get exactly the same, basically. So I would expect that in that regime, you will get the phases. But when you go to lower frequencies, then who knows? I mean, then you will not have probably sharp transitions, and it gets more complicated.
Well, for now, I would say that we definitely see a rather sharp localization transition. We haven't probe the non-ergodic phase, but I would say there doesn't seem to be any reason it shouldn't be there. Let me put it this way. I mean, yeah, the question I had was actually related to an extent to this question. So you mentioned, now there was a slide where you were discussing the that you need to adjust, if I understood correctly, that you need to adjust the size of your unitary matrix.
Yes.
To match the Rosenzweig-Porter. So could you repeat that? That I didn't quite catch. Yeah, here.
Yeah.
So.
Yeah. What the point is? Let's say if we look at the eigen. This is one slide before that.
Mm-hmm.
If you look at the eigenvalue and the eigenphase dynamics for the, let's say, for the Dyson Brownian motion and the circular Dyson Brownian motion, these are described by these equations. And what we want is that these equations, let's say, map on each other. So that essentially means that if we make an expansion of this tangent, that we get, let's say, just the argument of this. The point now is that if we have, yes, let's say, okay, no, sorry, let me put it more carefully. If we expand this tangent, then we get, let's say, up to, let's say, many level spacings. These equations are the same. The point is that if the density of states for the Hermitian and the unitary case are different, then this contribution does not match this contribution.
Yeah.
Let's say these terms depend on the density of states. If you now go to the Rosenzweig-Porter random matrix ensemble, then we see that the density of states in the middle of the spectrum is given by n divided by square root of 2 pi. While if we take the number of elements, sorry, the matrix dimension for the unitary case equal to m, then we see that the density of states is m divided by 2 pi. So if we take n equal to m, then let's say then we have different density of states for the Hermitian case and unitary case, and then this equation does no longer map on this equation. So to correct for that, what you need to do is you need to take m different from n such that, let's say, this number equals this number, and this you can do by choosing m equals the square root of n times the square root of 2 pi.
Okay. Yeah, I get it now. And
okay.
Okay. Yeah, and you also mentioned that so you're computing these matrices numerically. You don't know for now, at least, how if there's any analytical expression.
Yes, let's say we went in the literature a bit on this, and it seems that in general, let's say, except for some, let's say, very special cases, the density, let's say, the properties are not known analytically. You can, when it comes to the eigenvalues, if I remember correctly, you can get some analytic insight from the Collier-Sutherland model, if I remember correctly. The point is then you end up with equations which are for finite sizes, let's say, of comparable, let's say, complexity as diagonalizing, let's say, these matrices. So with that, you don't win too much, but maybe, let's say, people who are really into this analytical business can get some results on that.
And what, again, you also mentioned that so there was a limit on the system sizes you could reach due to some numerical issues. Could you elaborate a bit on that?
Yes. Okay. Let's say essentially. Okay. What we did numerically was we we used 10 to the 4 time steps. Let's say essentially when we focus on the largest system size, we took 10 to the 4 time steps, which turned out, let's say, by comparing, let's say, different numbers of time steps, that in this case it was converged out, let's say. So yeah, it was converged. But okay, then you need to do, let's say, 10 to the 4 matrix multiplications of dimension 1000, and that for each sample. So the computational costs, let's say, increase quite rapidly. So that let's say puts a bound on the matrix dimension that you can study. Another issue that we encountered, but which probably can be resolved, is that because at each time steps you're adding, let's say, a matrix, a very small matrix to a very large matrix, is that you also start seeing some issues with numerical precision, but by which, let's say, sometimes results just become complete nonsense. But okay, maybe by programming this a bit more careful, you can circumvent this.
Okay, let me ask actually, again, this is related to my first question. So what happens if you use the different density of states? So if you so my understanding is you need to choose the system, the matrix size. Yeah, here. So what happens if you just neglect the difference?
What you essentially get then is, let me think, if you take, yeah, what you then get effectively is that you, let's say, you can effectively think of this as that you evolve the system to a different time, which means that this factor gets replaced by something else which depends in some let's say non-trivial way on n. So you get still, let's say, an ensemble of the same let's say form, but with a more complicated prefactor. And by that, let's say, the ensemble also does no longer match the properties of the Rosenzweig-Porter random matrix ensemble.
So, I mean, in the simplest case, that would mean that the transitions will happen at different values of gamma, well, for whatever appropriate gamma would be there.
Yes, but I didn't go into this too much in detail, but I can imagine that also the position becomes matrix size dependent then. And that will be, let's say, less fortunate, because, let's say, then you cannot really draw a phase diagram to which you converge in the thermodynamic limit.
Okay, I see. Thanks.
We have also a question from Sang-Hoon.
Hey, so my question is that, I really didn't grasp on a connection between a Floquet operator and a unitary Rosenzweig-Porter ensemble. So in the beginning, you mentioned about about Floquet operator as a motivation for the unitary Rosenzweig-Porter ensemble, but when you dealing with the Brownian motion and thing, there is no periodicity at all. You didn't introduce some sort of a periodic time. So how can I understand those two ideas?
Yeah, and that's a fair point in this sense that the mapping is a bit indirect indeed. How you can think of it is that instead of, let's say, when you study Floquet systems, you typically look at, let's say, that the Hamiltonian, but now we only focus on let's say, the time evolution operator, which evolves, let's say, the Hamiltonian over single period. So if you want to, let's say, study, for example, dynamics of observables, this approach will not be appropriate to study, let's say, what happens within, let's say, one cycle, so between time 0 and time t, but only, let's say, what happens at integer periods.
Okay.
So in that sense, yes, the mapping is a bit indirect. I agree with that.
Okay, all right, yes.
Does this answer your question? Or?
So basically, you are taking only one cycle of unitary Rosenzweig-Porter ensemble, right?
Yes,
okay.
Let's say we have a random matrix ensemble which reproduces this thing, which brings you from, let's say, time 0 to time
1 over
period
n to the gamma, yeah.
1 period.
So the period is 1 over n gamma, right? Something like that in case of unitary ensemble, right? Unitary Rosenzweig.
Yes, let's say now the period is not really well defined in this sense, because let's say here the period really comes from a Hamiltonian. Let's say we integrate over one cycle, and here we entirely have no notion of a Hamiltonian, so also not really a notion of one's Floquet cycle, let's say.
Okay, yeah. Thank you.
You're welcome.
Do we have any other questions from the audience? Seems not. So in this case, let us thank Wouter again. And thank you all for joining. With this,